Welcome back to an Introduction to Real Analysis. Continuing in Chapter 3, we're now in Section 2, the title section, Continuous Functions. Now, a high school kind of description of what a continuous function is one that you can draw, quote, without lifting the pen from the paper, end quote. Now, that intuition is somewhat useful in simple situations, but we need to be a bit more rigorous. The following definition took many great mathematicians like Bolzano-Cauchy and finally Weierstrass, names we've seen before, to get correct, and its final form is really only from the late 1800s, so this took a while to get precisely where it is today. This definition is, suppose S is a subset of the reals and C is an S. We say that the function f, which maps S to R, is continuous at C if, for every positive epsilon, there is a delta, which is positive, so that for any x in the set for which x is within distance delta of c, then we must have f of x within distance epsilon of f of c. So for every epsilon which measures a distance in the range, there is a delta which measures distance in the domain, so that if in the domain you are that close to c, then in the range you are this close to f of c. When f is continuous at every point in a set S, you simply say the function is continuous on the set S. Now, if f is continuous on S, so it's continuous at every point in S, and A is a subset of S, there is an exercise that asks us to show that the restricted function is continuous on A. The converse doesn't hold in general. We will see an example of that in this section. Now, continuity is perhaps the most important definition to understand in elementary analysis. It's not a straightforward or terribly easy definition to get your head around. It's no accident that the definition is very similar to that of a limit of a function, which you may have noticed. The main feature of continuous functions is that these are precisely where functions behave nicely with limits. So here's a diagram. Here's the definition. Here is a function f of x. What does this definition mean? Here is x equals c, and here is y equals f of c. So what do we want? That no matter what epsilon we pick, but what is epsilon going to measure? F of x within epsilon of f of c. In other words, f of x should be in between f of c plus or minus epsilon. So this green tube represents all of the y values that will make this conclusion hold. Now that we've picked this epsilon and we know what we want to get out, we need to know that there is a delta that will force it to be true. So what we do is we look at all of the inputs that get us into the green tube. So here are some x values sort of picked out where we intersect the boundaries of this green tube. And if I very closely look just near x equals c, if I pick a little delta given by these purples, so x goes from c minus delta to c plus delta, we observe that if the input is taken from this purple region, the output is guaranteed to be in the green one. So it didn't matter what epsilon we picked, we found a corresponding delta, so that if we are within delta in the domain, if we're within distance delta of c in the domain, then we are forced to be within distance epsilon of f of c in the range. Now, delta depends on epsilon, but also depends on c. If I picked a different c, I might have been forced to pick a different epsilon. In terms of how this definition is put together, c is picked, and then epsilon is picked, and then there must be a delta. So delta is allowed to depend on epsilon, but also on c. Also, there's no requirement here that you somehow find the best delta. I intentionally drew this purple region. You could make it a little bit wider and still satisfy the definition. You don't have to be optimal here. You just need to show that a delta exists. So we don't need to account for every f of x that is within epsilon of f of c. This purple region misses tons of inputs that get us into the green region. We don't need to account for all inputs that give us so-called good outputs. We just need to show that every input close enough to c is a good input. So we only need to find some particular positive delta, so that for all x's within that distance of c, you must be in your range, f of x must be within epsilon of f of c. So let's get a proposition. Suppose f maps S to R and C is a point in S. Then f is continuous at C if and only if for every sequence in the domain converging to C, you must have the corresponding sequence in the range converging to f of C. Also, if C is not a cluster point of the domain, f is automatically continuous there. And if C is a cluster point of S, then f is continuous at C if and only if the limit as x approaches C of f of x equals f of C. So let's prove these three items. Now, item 2 is actually the most straightforward. If C is not a cluster point, so we need to remind ourselves what cluster points are, and then what does continuity mean. So if C is not a cluster point of S, then there is an epsilon, which is positive, so that given any y in the set, this fails. In other words, the distance from y to C must be bigger than or equal to epsilon. So there is some interval of radius, and here we've called it alpha, around C, so that there are no points in S in that interval. So it doesn't matter what epsilon we pick. If you pick delta to be less than this alpha, so further away from alpha is the only place you can possibly find points in S. So if you are closer than alpha, there are no points in S, except for C itself. That was part of the givens of proposition 3.2.2. So if C is not a cluster point of S, you can pick a sufficiently small delta so that the only point in S that is within delta of C is C itself, in which case f of x minus f of c will simply be 0 because the only allowable x is C itself. So that's pretty straightforward, but also kind of silly and basically won't come up. So we're not really going to consider continuity at points that aren't cluster points. The definition is essentially vacuous at this point, and it requires there to be points in the domain of a function that are not cluster points of the domain, which you of course can construct and can happen, but are fairly exotic and artificial. So instead, let's consider the third item. Suppose you are a cluster point. Now, the only distinction between having a limit being L and fixing L to be f of c is that in the definition of limit, you are not allowed to pick x equals c. However, the definition of continuity allows that choice. But if the limit of f of x equals f of c, then continuity follows quite quickly. We can guarantee f of x to be very close to f of c for every x that is close to c but not equal to it. But if x equals c, you get a 0 here, in which case this inequality automatically follows anyway. However, if f is continuous at c, this inequality holds for every x within delta of c, whether x is equal to c or not, so it definitely applies when x isn't equal to c. Which means the real point here is attempting to prove item 1. And this is the one we're going to use most frequently. If C is not a cluster point of S, any sequence in S converging to C must eventually all be equal to C, right? If you're not a cluster point, then you can't get very close. So if you have a sequence converging to C and it's not a cluster point, since points in the set S can't be that close to C, if they're converging to C, they must be equal to it. So if all of the xn's are eventually equal to C, then all of the f of xn's are eventually equal to f of C. Again, if you're not a cluster point, there's not a lot to say here. So when C is not a cluster point of S, continuity at C in this statement are kind of automatically satisfied, making them logically equivalent. Instead, let's turn our attention to when C is a cluster point of S. Now we're going to use lemma 3.1.7, which you may have seen coming. This was our result that tied limits of functions with limits of sequences, which appears quite relevant. Now we're just going to use that limit being f of c. So here was that lemma. So the distinction whether you're allowed to let xn equal c or not is not all that important. In this definition, you couldn't let xn's equal c. But the conclusion was that the limit of f of xn equals, and now we're going to put f of c there. Well, if a bunch of the xn's equal f of c, you just get f of c interspersed in that sequence. So it doesn't really change very much. If the claim holds, allowing the possibility but not the requirement of xn equals c, then if you remove the possibility of xn equals c, it definitely still holds. Similarly, if it holds forcing xn to not equal c, introducing the possibility of some of these terms flat out equaling f of c will not change getting out that limit. So we proved the previous proposition really by leaning in a somewhat informal way, I'll admit, on earlier results. So we quickly proved a whole bunch of properties of limits of functions by simply citing earlier results regarding limits of sequences. Now that we've shown continuity at a point is equivalent to a limit of a sequence being the correct value f of c, at least when c is a cluster point of the domain, and we can tie that into limits of sequences, we're just going to lean on those results to get some quick claims about continuity. Specifically, suppose f and g are both continuous at some point c in their domains. Then f plus g is continuous, f minus g is continuous, the product and the quotient are continuous as long as you are not attempting to divide by 0. Okay, a modified proposition. Suppose f of x equals p of x over q of x, where p and q are specifically polynomials. Then f is continuous on its entire domain. In other words, everywhere the denominator is not 0. So let's prove this little modified proposition. We're going to bring back prop 3.2.5. If we have two continuous functions, then their quotient is continuous as long as you're not dividing by 0. So we just need to establish that the polynomials p and q are continuous everywhere. However, f of x equals x and g of x equals c are continuous everywhere. Those follow from part 1 here. First, let's consider f of x being a constant. A constant is continuous if and only if, for every sequence approaching c, f of the sequence approaches f of c. Well, if the constant is capital C, any sequence converging to little c, you'll just get out a constant sequence of capital C's converging to capital C, which is f of c. Similarly, if f of x equals x, if xn converges to c, xn is f of xn and c is f of c because f is the identity function. So you get property 1 establishing that the identity function and constant functions are continuous everywhere. But then, by multiplying x's against themselves, multiplying by constants, and then adding and subtracting such terms, you can generate any polynomial. So prop 3.2.5 and 3.2.2 give us all polynomials are continuous everywhere, and therefore all rational functions are continuous everywhere that the denominator isn't 0. Let's take a look at another example. Sine and cosine are continuous. Now the proof relies on the following trigonometric identities. Sine x minus sine c is this particular product. If you know the sum and difference formulas for sine, like sine of a plus b is sine a cos b plus sine b cos a, those sorts of things, apply them both to this sine and this cosine, and you can recover this form here. Similar for cosine. Okay, so these are called sum to product identities. It takes this difference of signs and transforms it into a product of a sine and a cosine. This difference of cosines can be transformed into a product of two different sines. We also need the following identities. The absolute value of the sine of x is no larger than absolute value of x, but it's never bigger than 1, and similarly the absolute value of cosine is never bigger than 1. Now, both of these are essentially by definition of what sine and cosine are. This one does take a little bit of thought, but we're kind of leaving it aside. So let's take a look at sine x being continuous. From the sum to product identity, we get the following. It's just equal. Now we split this up by factoring that absolute value across various different terms, and we say that this cosine term in absolute value is less than or equal to 1. Now finally, the sine of something in absolute value is no larger than the absolute value of the thing you were taking the sine of. That was another trigonometric identity we had on the previous slide, and then these twos cancel out. So the absolute value of sine x minus sine c is no larger than x minus c. Therefore, if xn is approaching c, by the squeeze law, you'll get sine of xn approaching sine of c. So sine is continuous at c, and c was arbitrary. What about cosine? Pretty similar, sum to product, distribute that absolute value everywhere. One of those sine terms you get rid of by saying an absolute value it's less than or equal to 1, and then you use that sine identity again, and now you have the same argument. If xn is approaching c, this absolute value is less than or equal to something approaching 0, so this is squeezed down to 0. In other words, if xn is approaching c, cos of xn is approaching cos of c, and we have continuity. Now, you've probably already realized one of the more basic tools in constructing complicated functions is composition. Products and scalar multiples and sums and differences get you polynomials, and then quotients get you rationals. But if all you have is the identity function and a constant, that's really all you can build until you start throwing compositions in there. I mean, we've got sine and cosine now, but what about sine of x squared? Or what about the sine of x squared? We can't touch those yet. We need functional composition to get that. So for two functions f and g, the composition f of g is just defined like this. F of g of x is f of g of x. Now, a composition of two continuous functions is continuous. This is a very key result. We'll prove it right now. Suppose you have a and b, two different subsets of the reals. F maps b to r and g maps a into b. So you can define the composition f of g. Let's assume g is continuous at some point in its domain, and g of c, so c is in A, g of c is therefore in B, assume f is continuous at that point. Then the composition f of g is continuous at c. Proof of this proposition is actually pretty fast using results we already have. Specifically, we're going to use this previous proposition, 3.2.2. We're going to let xn approach c, all living in the domain of g. Now, g is continuous at c, so since xn is approaching c within its domain, g of xn must approach g of c. But since g maps a to b, all of these g of xn's are in the set B. So now I have a sequence of numbers in the set B approaching g of c. But f is continuous there and its domain is b. So since this sequence in B approaches this value, f of that sequence must approach f of that value. Altogether, if xn approaches c in the domain A, then f of g of xn must approach f of g of c, and we're done. That's all there is to it. We have done a lot of legwork and we're starting to see the rewards. Let's take a look at an example. Sine of 1 over x all squared is continuous on the interval from 0 to infinity. Why? 1 over x is a rational function. We've already argued rational functions are continuous everywhere that they are defined. That includes the interval from 0 to infinity as long as you don't include 0. The sine function is continuous everywhere. We already proved that. Therefore, within the range of h, it's definitely continuous. And the squaring function is a polynomial. We've shown polynomials are continuous everywhere. So we compose squaring with sine with reciprocal, and we have a composition of various continuous functions, must be continuous on the interval from 0 to infinity. Now, if you were to attempt to prove that the sine of 1 over x all squared is continuous at any particular point straight through the definitions, it would be kind of a nightmare. I wouldn't even try. Okay, what about discontinuity? If f isn't continuous at a point, you simply say it's discontinuous or has a discontinuity. So it's just a negation definition. We've already seen that an equivalence of continuity exists in terms of sequences, so we get an immediate result. Suppose you have a function defined on a set S, and C is an element of that set. F is discontinuous at C if and only if there is a sequence xn which is converging to C, but f of xn does not converge to f of c. Okay, meaning either that second limit is something else or doesn't exist at all. So example 3.2.10, the Heaviside function, which we've seen before, the function that jumps from 0 to 1, is discontinuous specifically at 0. So if we take xn to be minus 1 over n, so minus 1, minus a half, minus a third, those are definitely approaching 0, But f of negative numbers is 0, so f of xn is constantly 0. So what is f of xn approaching? 0. But that isn't equal to f of 0 equals 1. So since we have a sequence converging to 0 in the domain where the corresponding sequence in the range is not converging to f of 0, it's not continuous there. Now what one could do is take 1, 1/2, 1/3, 1/4. In that case, you'd have a sequence converging to 0 where f of xn is 1, and then it would appear that f of xn does converge to f of 0. But one particular sequence having this convergence happen is not enough. To get continuity, you need the correct convergence in the range to be happening for every sequence converging to C in the domain. So finding one sequence in the domain converging to C where the corresponding sequence in the range does not converge to the correct value is enough to disprove continuity. What about example 3.2.11, the Dirichlet function? What is that? This is the function. It jumps between 1 and 0, but in a really nasty way. At rational numbers, it evaluates to 1, and at irrational numbers, it evaluates to 0. We claim this function has no points where it's continuous. At every point, it is discontinuous. That sounds like a lot to prove, but it's actually not so bad. Pick any number you want. We're going to show at x, it's not continuous there. We have an old result that says in any interval, there are rational numbers, but there are also irrational numbers. As a consequence, you can approach x with rational numbers, but you can also approach x with irrational numbers. So I have two different sequences, xn and yn, both converging to x. All of the xn's are rational, all of theyn's are irrational. Therefore, all of the f of xn's are 1, and all of the f ofyn's are 0. So this sequence is constantly 1, it converges to 1. This sequence is constantly 0, it converges to 0. They can't both be converging to f of x. So at least one of them is a sequence converging to x in the domain, not converging to f of x in the range, and one such sequence existing means the function is not continuous there. Where were we talking about? An arbitrary x. So the function has no points of continuity. So we have a function now that is discontinuous absolutely everywhere. The Heaviside function was a function that was continuous except at a point, and it just has like a jump there. Can we come up with a better, more interesting example? Let f of x be defined this way. If you have an irrational number, you spit out a 0. That much is like the Dirichlet function. If, however, x is rational, first make sure it's in reduced terms, meaning k is a positive integer and m and k are relatively prime. Then you spit out 1 over k. So if you pick x equals 1/3, you would say 1/3 is the output. If you pick x equals 3/9, you would say that's not reduced. First reduce it down to 1/3. That's how you make sure this function spits out unique values. We claim this function f is continuous exactly when x is irrational and discontinuous exactly when x is rational. So we can construct a function where the set of discontinuities is not just isolated points, it's all rational numbers. So suppose you pick a rational number and let's assume it's in reduced terms. We can take a sequence of irrational xn's approaching x. Okay, we've already established that you can make a sequence of rational numbers converging to x and a sequence of irrational numbers. We're doing irrationals in particular. Since we're approaching with irrational numbers, f of xn is constantly 0. So f of xn converges to 0, but f of x is not 0. So the function is definitely discontinuous at rational numbers. Okay, so here is our function, and it is discontinuous for rational x. So let's let x be irrational. We want to show it is continuous there. First, I'm going to stick x between two numbers m and m plus 1. Now, let epsilon be positive. We're attempting to show continuity at x, so that begins with a for every epsilon. So let epsilon be positive. We're going to go ahead and assume epsilon isn't just positive, but that it really is small. It's less than 1. Pretend you have an arbitrary sequence xn converging to x. We need to show that f of xn converges to f of x. Since x is irrational, we need to show that f of xn converges to 0. So since we want to show f of xn converges to 0, we're going to do a limit of sequence problem. Let epsilon be positive. Take k large enough so that 1 over k is less than epsilon. Now, We have x between m and m plus 1. That's an interval of length 1. We're going to give ourselves a little extra wiggle room, m minus 1 and m plus 2. So now I have an interval of length 3, m minus 1 to m plus 2. X is definitely inside that interval, and it's at least distance 1 away from the left endpoint and at least distance 1 away from the right endpoint. Basically, our goal here was to make an interval of finite length, and x is not terribly close to the ends. So now I have an interval of length 3, m minus 1 to m plus 2. How many rational numbers whose denominator is 1 are there in that interval? Finitely many. How many rational numbers with denominator 2 are in this little interval of length 3? Finitely many. How many rational numbers with denominator 3 are in this interval of length 3? Finitely many, and so forth and so forth. In other words, as long as I'm only allowing rational numbers whose denominator is up to this constant k, there are only finitely many of them in between m minus 1 and m plus 2. Since epsilon was less than 1, that means there are only finitely many of them within epsilon of x. That was the point of making sure x was more than distance 1 away from this number and more than distance 1 away from that number, and epsilon being less than 1. So as long as epsilon is less than 1, which it is, there are only finitely many rational numbers pretty close to x whose denominator isn't that big. What does that mean? If xn is approaching x, okay, now x is an irrational number, there are only finitely many rationals nearby x whose denominator is fairly small. So once I let epsilon be small enough, I have missed all of them. As long as epsilon is sufficiently small, in other words, as xn is getting closer and closer to x, if it is a rational number, the denominator has to be very big, bigger than the k, capital K, we picked on the previous slide, meaning 1 over that is less than epsilon. Therefore, as xn approaches x, if xn is irrational, f of xn is definitely 0, but if xn is rational, f of xn is still less than epsilon in absolute value. So since the absolute value of xn is eventually less than an arbitrary epsilon, f of xn must approach 0, which is f of x. The key here is that for our irrational x, if you only put down integers, x is not terribly close to any integer. If you zoom in enough, it looks like it's far away. Okay, but what if you put integers and half integers? Again, if you zoom in enough, it looks like it's not close. If you put in integers and half integers and third integers, in other words, rational numbers whose denominator is 1 or 2 or 3, if x is irrational and you look close enough, you have missed all such numbers. So whatever epsilon is, make k really, really big so that 1 over k is less than epsilon. Zoom in close enough to x so you don't see any of those rationals. Xn still has to eventually get closer than that. So if these are rational, their denominator is so big that 1 over k is still less than epsilon. Therefore, f is continuous at irrational x. We've made a very weird function. It's continuous on irrational points and discontinuous on rational points. So the rather interesting function from the previous example is called the popcorn function. And it has period 1. So if x is 2 over 3 or 5 over 3 or 8 over 3 or 11 over 3, you get out the same value. If you add 1 to x, an irrational is still irrational. And if it's rational, you haven't changed the denominator. So the function is periodic with period 1. If I only graph it between 0 and 1, it looks like this. Here are the heights it takes. A half gets mapped to a third and 2/3 both get mapped to 1/3. 1/4 and 3/4 both get mapped to 1/4. 1/5, 2/5, 3/5, 4/5 all get mapped to 1 over 5, and so forth. So here's what the function looks like. For irrationals, it hangs out down at 0. 1/2 gets mapped to a half. A third and 2/3 get mapped to a third, and so forth. Now let's define g of x as the following function. It's 0 except at a single point. G is discontinuous exactly at that place where it has this jump, but it's continuous everywhere else. So as a proof, if xn is 1 over n, that definitely approaches 0. Since none of them are equal to 0, g of xn appears to be constantly 0, but that's not g of 0, which was equal to 1. So the function g is definitely discontinuous at 0. But anywhere else, Anywhere else, if xn is approaching x, then it's not 0. If my cursor is hanging at my point x, to approach this cursor, I have to eventually not be 0 because I'd have to be close. And it doesn't really matter where x is. Eventually, you're non-zero. Therefore, eventually g of the sequence is 0, and that is the value of g at every other point. So this function is continuous everywhere except at the single place where it takes so-called the wrong value. So we have a function now that is discontinuous at a single point. But this is what's called a removable discontinuity. Was it discontinuous there? Yes. But if you just kind of change the value to be what it should have been, you can make this into a continuous function by changing the value at this one single isolated point. So in cases where the limit of a function exists, either the function is continuous at that point or it has a removable discontinuity because you could just redeclare what the value of the function is and call that f of c. So when the limit is either infinite or doesn't exist, you can't do this trick. So if the limit as x approaches c of f of x is infinite or doesn't exist, you don't have a removable discontinuity. It's called a non-removable discontinuity. Note also in this example, if you make a restricted function, by restricting the domain so much that this is the only point in the domain, then this is no longer a cluster point because you cannot approach 0 without using 0 if that's the only point in the domain. And at non-cluster points, functions are automatically continuous. So if you restrict the domain enough, you can turn this into a point of continuity. But at this point, the domain is so restricted that it's kind of silly. It does, however, remind us that a function on a restricted domain can have limits, whereas the original one didn't, which is also now manifested here as a function on a restricted domain being continuous where the unrestricted function is not. So continuity of f at a single point, in one sense, it's not a huge deal. It's basically our previous definition of having a limit and declaring that the limit should have the correct value with a couple of modifications, but that's really the main gist of it. But continuous functions are really the cornerstone of what we're going to be studying. So it is a big deal. Upcoming theorems regarding continuous functions are really crucial foundations for what we're going to establish about derivatives and integrals and things that students tend to think, oh, that's what calculus is about. Why haven't we said the word derivative yet? We're already in chapter 3. You need to lay a lot of groundwork, and honestly, if you're doing analysis, continuous function is like the atom that you study.